Good afternoon. Welcome to Krishna's class. Before I introduce the trigonometric series, we want to make certain remarks on what we did in the previous lectures. In fact, what we did was the core of the results that we proved was that a Hilbert space is isomorphic to L2A for some index set. We have in fact done the entire detail, but I want to revisit the whole thing and just make some remarks and compare with some of the elementary isomorphism theorem that we did in the case of vector space. I think I have made these remarks earlier, but still I want to stress it once again for clarity. Okay, and just have a comparative statement also. So for any finite dimensional vector space, V over F of dimension n, V is isomorphic to a copy of F. Because if the isomorphism is not unique, when there are several isomorphisms that you can do. And how does this come? It comes like this. It is an n-dimensional. So let Un or Vn, V1 be a ordered basis for V. Then for every V, there exists scalars. Here elements from F, C1, such that V is equal to C1 V1 plus and this is a unique representation of V in terms of the chosen ordered basis. Okay, because if you choose a different ordered basis, you will get a different representation that we are all familiar with. Now we define F1 by and this is an element of where C1, C2, Cn are picked up from the coefficients that appear here, and we have chosen an ordered basis, therefore it appears in that format. Now then we have phi is an isomorphism of V or this is a special isomorphism that we have that is associated with the ordered basis that we have chosen. If you choose a different ordered basis, you will get another isomorphism. So there are several isomorphisms possible from V to Fn. But what is important is that there exists an isomorphism, or in fact, this gives Fn gives a replica of the vector space V in concrete terms. Okay, that's about that. Now we come to the case of H. Let C or R, no, that's not matter. Okay. We are taking Hilbert space over C. Then H is isomorphic to L2A or and we have defined what L2A is. We shall see soon what exactly it means. See, what you have is the following. See, you take a U belonging to X. Let U alpha belonging to the index set A, some index set A, be a maximal or complete orthonormal now this is the important part. We have what we have proved, the last result that we have proved is that if H is a Hilbert space, there always exists a maximal orthonormal set in H. So the existence is no problem. And in fact, there are several such possible maximal orthonormal sets. It is not unique. Now this is important. Now let U alpha hat, I'll use a slightly different notation, be equal to the inner product of V with U alpha. And this is a complex number or a real number, depending on whether it's a complex Hilbert space or a real uh, inner products, real Hilbert space. So this is for every alpha belonging to the index set A. Index set A comes from here. Okay. Now define phi from phi of V V hat alpha belonging to A. Okay. So we define phi V equal to V hat alpha for alpha belonging to. This is the map phi that we define. So you know that this is an element of A and this is V is an element of H. Okay, then of on to L2A is also a inner product space whose typical elements are of this type. Okay. Something like the collection of C alpha where alpha belonging to A. Now I want to make one remark. See, this A, the index set need not be finite or countable. It could be even uncountable. Does not matter. Now this is not essentially causing any problem because you see that what we have is this. You look at the one of the conditions that you have is that the on these scalars is that we have summation over alpha So one of the conditions that we have is this following on this, that see now you know that there's nothing alarming about it. This could be an uncountable, A could be uncountable. But what you have is that V hat alpha is not equal to 0 for at most countably many alphas when this condition is satisfied, and that really depends on the particular V that you choose also. Okay, so that's one of the crucial results that we have proved that. So this, what we have proved is that this is the isomorphism that you have, identifying phi v defined by this. This is an isomorphism. An isomorphism is essentially a one-to-one onto map, and these are two linear spaces. So it's a linear map. Moreover, it's also a Hilbert space isomorphism. That means the following. That is, if U and V are two elements of conjugate. Okay, it's actually this is the inner product in L2A, and the inner product of U with V in H is the same as the inner product that is obtained through this process. Okay, so it's the complete structure of the Hilbert space is reflected in the copy of L2A that we are picking. Once again, the choice of isomorphism is not unique. Now you compare the two situations, finite dimensional vector spaces and Hilbert spaces. It is the same result that we are proving. Okay, but then we have to identify the right kind of image space. The image space in the case of finite dimensional vector space is Fn, which will be Cn if we are using C as the field, or Rn if we are using R as the field, or any other that you are using. So in general, Fn for any field that you are using. And here the corresponding part is this. Okay, phi maps V to an element which is in L2. Okay, right? And you have picked this. How it comes from this. U is written as, or V is written as and then use orthonormality, and you get this as C V hat alpha is what you have. So compare this with the finite dimensional case. Y. Okay, then we put in that case E is the order n tuple which comes as the coefficients here. You see that these constants are uniquely determined once you choose the ordered basis. Okay, right? So compare this with this one. Okay, compare this with this one and compare this with what you have, this one. Okay, so I just wanted to bring this remark. So it is essentially something we are familiar with in the finite dimensional spaces. We are trying to explore a Hilbert space where it is possible to explore it, and it needs a lot of work because we have to prove we have to introduce concepts like maximal, orthonormal set in the Hilbert space and show that such a set exists. Okay, so I think I'll leave it there. Now, what we start work on is a more concrete example, nothing abstract about it. We something on a familiar ground of what are called trigonometric functions. Okay, right. So let us now introduce the so-called trigonometric series. Start with our basic definitions of a trigonometric series and then work on that. So we want to look at the manifestation of the theorems that we have done in some specific situations which lead to the Fourier series. Okay. So we define the following. So let T designate that is mod z is equal to 1. In the complex plane, this is T. Circle with center at the origin and radius 1. This is T. Now we define following. Let f from P to C any P is the domain. Now we define f on R1 is the real line. This is the real line, R1. On R1 by Ft equal to capital F of. Now e to the power it is some point here. Is some point over here, and as t ranges over, this is which is equal to cos t plus I sin. This is some point here. Okay. Now what is happening is the following. So f is defined on this. So using that, you can define ft to be f of e to the power it. Okay. F of e to the power it is, so t is over here. Okay. Now you see that if you take from minus pi to plus pi, see that if you move from here to here, as t changes from minus pi to plus pi, you see that e to the power it just goes around this circle. Therefore, primarily, you see ft is defined as, so this is some t. Okay. Well, when you say from minus pi to plus pi, or you can write it as 0 to 2 pi, all the same, because finally periodicity is going to take care of everything. This is 2 pi. Okay. So, as t moves from 0 to 2 pi, see, it is going to come somewhere. This is the map that you have, e to the power I. For corresponding to each t on 0 to 2 pi, there is a unique point on t. Okay. Now f is defined on this, capital F is defined on this. Therefore, f of e to the power it you set as f of t. So for initially, but one thing that you observe is that e to the power it equal to e to the power I to n pi. Therefore, you see that it not only defines for points in 0 to 2 pi, but to every point t on the interval r. Okay. Every point t on the interval, there will be a corresponding e to the power it, and because of this periodic nature of this function, you have this. Therefore, f of e to the power I t plus 2 pi 2n pi e to the power I t. Therefore, what you have is the following. This is equal to f of, by definition, and this is equal to f of so every t on this, so every point, if you take a point P on R, P is equal to some n, and t of course chosen that is such a unique choice. I mean, this is the reminder when you define, you have a it's a point P is a real number, and that real number divided by 2n pi, and this is the remainder. Okay, so it can be written in this uniquely in this fashion. So there is a unique value of t determined like this, and therefore f of t plus 2n pi is well defined and given by f of t, or f is a periodic defined on R1 so this is the definition of f. So what you do is take any t here, that t is of the form 2n pi plus t, where t lies between, or you take any point P here, that point is of the form t plus 2n pi, where t lies between 0 and 2 pi. Okay. Then what one does is f of t plus 2n pi turns out to be f of t, because the way in which we have defined capital F. Okay. Therefore, you see that the small f that you create out of capital F turns out to be a periodic function with period 2 pi. This is what you have. F is a function on R1 with period 2 pi. There exists a capital F from t such that f of so we can transfer the game from the real line to the circle or from the circle to the using this. Thus, on T, that is the unit circle, may be identified with periodic functions. This is important. Now we introduce LPT. Now we define what is called LPT. We define LPT as follows. The set of all F complex valued, Lebesgue measurable, Lebesgue measurable, and 2 pi periodic functions R1 such that this property is there, 1 by 2 pi finite. Okay. Having this condition, this integrability condition for okay, so that puts the restriction on the function. So this is like a LP mu, where mu is a Lebesgue measure on 0 to 2 pi or on T divided by 2 pi. Okay. Now we define L infinity to be periodic complex valued functions on T we put a restriction also. We take continuous complex valued 2 pi periodic functions R1 with the norm Now this is actually in fact a so this has automatically the following property, that is integral minus pi to pi, or what you call supremum over T finite. Now this is automatically okay. Now in the case of LPT, in the case of LPT, we define norm of F P 1 by 2 pi P as the norm. And norm of for L infinity finite. Okay. And this is finite. Okay. Therefore, we have L infinity equal to 1. That's why this dividing factor has come. This is 1, then you see that what you get would be 2 pi, and 2 pi cancels with that, and f identically 1. So also for this is also true for infinity. Okay. Now we work on L2. Equal to 2. So we define what's a trigonometric polynomial. Define what's a trigonometric polynomial. A trigonometric polynomial is a finite sum of the form Bn sin n for t belonging to R. are complex numbers. This is what you call a trigonometric polynomial. Now ft can also be written as a simple exercise, can also be written as summation minus n to n Cn e to the power a into t. For trigonometric polynomial. Now you can connect these Cn's to the scalars a0, a1, a2, an, and b1, b2, etc. Okay. So one can identify the relation between these two, and that's something which you can work out. Now this is what is called using identity. Identify these apparently different for instance, C0 is going to be N. Okay, that you can compare the coefficients and get the results. Okay. Now we get some orthonormal sequences. Let n belonging to Z. Now consider L20 we have the inner product on L2T by inner product of F with G equal to 1 upon 2 pi integral minus pi into pi dt. So this makes L2T an inner product space. Okay. It's an inner product with this inner product. Now we have the inner product of UN with UM, where UN is given by this. Okay. So then the inner product of UN with UM is equal to 1 upon 2 pi integral n minus m and this turns out to be 1 and our zero whenever n is different from thus UN It's an orthonormal sequence. It's an orthonormal sequence. It's just L2. This is called the trigonometric. Now we prove that a maximal or complete orthonormal or in other words yield is a Hilbert space. This is a concrete example that we plan to work out. This particular example has a lot of significance. In fact, you see the whole Fourier series is centered around that, or probably the genesis of these thoughts came from this trigonometric, the special properties of the trigonometric functions. Okay, so thank you very much. So we have to prove this one, that this is a maximal orthonormal set. Thank you very much.